And what I want to show you is that there's one general mathematical tool that you can bring in once and use it for all this different stuff. So this is the kind of mathematical tool that you would use if you are doing something similar to this, dealing with oscillation in an upper division level engineering or physics class. And it starts out with something that I keep saying this, but very few people seem to remember it. Something that you are supposed to have covered in pre-calculus trigonometry. It starts out with this Euler's formula, which says e to the I theta, meaning exponential of imaginary number I times some variable theta, is equal to cosine theta plus I sine theta. Do people remember seeing this? Euler's formula. Outside of physics 4b, where you would have seen it when I brought it in. Wait, did I bring? Yeah, I started doing this 2 semesters ago, so all of you should have seen it if you took my 4b. But even if you haven't, you saw this in trigonometry, right? Yeah. And now that you have taken calculus 2, you can actually prove this. Let me just say how without doing it, taking time. You can prove this using Taylor polynomial. Write out the Taylor expansion of cosine theta. Write out the Taylor expansion of sine theta. Write out the Taylor expansion of exponential while being mindful of this fact. I raised to the power of 0 is 1. I raised to the power of 2 is minus 1. I raised to the power of 3 is minus I. I raised to the power of 4 is plus 1 again. And then it repeats from then on. So when you write it out, write out first 8 terms or so. Then you will see that this left-hand side is equal to this right-hand side with this I, giving you all the terms that still have I left in it. Well, I skipped I raised to the power of 1. So this I will give you all these terms with the I still in it. And you can show that for yourself in like 20 minutes just writing it out. So what I want to, yeah, good? Okay, does anyone need any explanation of Euler's formula? So this is it's the first example you see of something that mathematicians do a lot, where they extend a known special function to a greater domain than when they were originally introduced. When they originally introduced the exponential, that was as a limit of, I guess, e to the x was introduced as a limit of n going to infinity. What is it? 1 plus x over n raised to the power of n, something like that? Is that right? Yeah, when x is 0, this is 1, x is 0, this. Yeah, so that's how it was introduced initially, right? And what you can realize is that even though when they were originally introduced, it was in the context of interest rate or whatever, x was just assumed to be real. But when you look at this, there's no reason to assume that x is real. Nothing forces you to. So x could easily be imaginary. And when it's imaginary, you could imagine this being I theta. And when you do that, this is the formula you get. That e to the I theta, and sort of working out the consequence of writing this out, you get that you could re-express this in terms of 2 real functions, or 1 real function, cosine theta, plus imaginary number times sine of theta. And mathematicians prove this, so I won't go through it. I don't have the time and I don't want to. So the reason I bring this in is because of the intuition about complex numbers, and is in particular periodic functions that this particular representation provides. Let me first show you the intuition about complex number, that this provides. And the guide here is the fact that when you write this out, you get cosine theta and sine theta. When you hear the word cosine theta, what do you think about? Like, what's the first thing that you associate with the cosine of an angle? Adjacent? Okay, that's one. Sorry, I'm trying to do something that I normally stay away from. So when you say adjacent, you are talking geometrically, without figures, without having defined any coordinate axis. Right? Let's say we are dealing with a coordinate axis, x and y. When we say cosine of an angle, which axis are we talking about? X, right? So this cosine theta, which multiplies to the real component, 1, you can sort of naturally associate that with x-axis. And something similar for sine theta. So when you have a point, let's say a particular point here, which is at some distance r, then if I'm talking about 2D plane, xy plane, this is how you would describe this. I have some vector r, and the x component of vector r, this is angle theta. X component of this vector would be r cosine theta, and the y component of this vector would be r sine theta. Right? Everyone here has pretty good intuition about geometry. And what I want to tell you is that I can use this same exact figure and change just a couple labels to show you something that you have seen in the context of complex numbers. I can say, instead of this being the x-axis, this is really the real axis. Instead of this being the y-axis, this is my imaginary axis. You have actually seen this before. And if you have a point here, the way it would be introduced in your math classes, this point is, it has coordinates A and B, or you would express that as A plus IB. Is this sounding familiar to anyone? And with this coordinate representation in mind, you could say that this is the Cartesian representation of the complex number. This A would be the x component, and this B would be the y component. And what this can give you is it's the polar representation of a complex number. So let's say you have this complex number here that you can express in two different ways. Complex number z. The first time you saw it this way. You saw it as A plus IB, right? This is what we can, I don't know if your math teachers use this language. This is what a physicist would call Cartesian representation of this complex number. Representation. Or rectangular representation, because you have x and y coordinate. Yeah? And if we have a vector, so it's representing the x and y coordinate. Second way of expressing the same complex number is, instead of specifying the component, I can give you, I still need two parameters, but I choose parameters differently. Instead of x and y components, I give you length and direction. That's the polar coordinate. When you are talking about vectors, length r pointed in some particular angle, theta. That's what that representation in the physical vectors is. You can think of complex numbers being similar. Instead of this being A plus IB, I can write it out as length r times e to the I theta. R gives you the length of the vector. So this is the polar representation. Polar representation. R gives you some kind of length of a complex number. And e to the I theta, well, the theta gives you the direction of that, the complex number, if you can say that. Let me write out one last term that will maybe help make the connection more concrete. Let me just plug this in and expand it out and write out what it is. So plug this in and expand it out. This is what I get. R times cosine theta plus I times R sine theta. This is my, or rather this is my x component. Or since we're talking about complex numbers, this is the real component. And this is my y component, or my imaginary component. This one-to-one match is direct. It's anything you can express as two-dimensional vector, you can express it as a complex number. And anything complex number can be used to represent any two-dimensional vector. There's this is not some spurious connection I'm making. It's so the complex plane that you have seen, that is the geometric representation of a complex number. And to make the geometric aspect more concrete, this is the thing that would make the geometric features more clear. Yeah?
Doesn't that imply that e to the I theta is never going to be bigger than 1? Or
No, theta can be anything, because then theta wraps around, right? Sine theta, like theta can be 1,000,000.
but e to the I theta, that gets capped, right? Because
Um,
sine theta.
So you want to be able to say this. You want to be able to say, when I have e to the I theta, that it defines a unit circle. That somehow when you square it, that it's never going to be, it's going to be actually exactly 1. That's what you want to say, right? Now here's that's a good intuition. So that's what we want to do. Let me just point out the slight difficulty that you run into, and we will find a way around it. So the slight difficulty that you will initially run into is, let's imagine calculating e to the I theta squared. So I have e to the I theta, and let's say I just want to square it. So it would be equal to, well, let me plug this in. So cosine theta plus I sine theta. Take that, square it. It's equal to, so cosine squared theta. This thing squared, so that would be minus sine squared theta. And then there's the cross term, cosine theta times the sine theta. There's two of those. There's I2, so it's a plus 2I cosine theta sine theta. Is this what we wanted? Like, does this fit with this description that we are using? Not quite, right? Couple things are. So we wanted the length of this to be 1. We didn't want it to be function of direction. So what all that this is showing is that apparently this is not equal to length. So the operation that you need to get length of a complex number is a different operation. Let me close that blind while you're thinking about it. The glare's in my way. Like, what other mathematical operation would you do so that you get something that has the correct property for length? Do you guys cover absolute value or modulus of a complex number in trigonometry?
Conjugated number. Conjugated number of the
Yeah. So this is the operation that's defined in that you define as a modulus or whatever. So let me just refresh your memory. So when you start dealing with a complex number, take the complex number squared. That actually doesn't mean much. That's not used very often. That's in contrast with a real number squared. Because a real number squared gives you always positive number. But if this is complex number, this is not guaranteed to be positive. I mean, look at it here. If sine theta is bigger, then this number will become negative. So the operation that is defined when you start learning complex number, using complex numbers more, is something absolute value squared is defined this way. It's defined as the complex number multiplied with something called it's a complex conjugate. And this is how complex conjugate is defined. Complex conjugate is defined as, I don't know, it's easier to describe it in words. Take all imaginary numbers in G and turn it into minus I. That's what complex conjugate is. So for example, if G is equal to A plus IB, where A and B are real, that's important, then the complex conjugate is A minus IB. Okay? And what I want to claim is that this complex, this absolute value squared here, this is equal to length squared. And let's see if this has the correct property that we need for length. Let me do the same calculation that we did here. So instead of this being I guess G squared, so or e to the I theta squared, what it would be is G, so e to the I theta times the complex conjugate. So it would be e to the minus I theta. Theta is real, so I can just do that. So e to the e raised to power of x times e raised to power of minus x. That feels to me like 1, isn't it? Everyone here feels comfortable with this particular calculation? If you do, great. If not, on your own time, try expanding this out. You will see that when you expand it out this way, this becomes plus, and the cross terms actually cancel out. So cosine squared theta plus sine squared theta, that is 1. So you do get so this does represent a unit circle, or the points along the unit circle.